Let's look at some examples of solving trig equations that are going to require us to use some identities. So in this first example, we have 4 times sine squared x plus 2 cosine squared x is equal to 3. So this is different than the previous examples that we've seen because we have both a sine squared and a cosine squared. And so we can't just isolate and combine like terms or factor or anything, at least not yet. And so we need to figure out how can we replace either the sine or the cosine with a matching term. So we can write everything in terms of sine or everything in terms of cosine. Okay, and then we can try to factor and simplify. So as soon as I see a sine squared and a cosine squared, I'm immediately thinking about our Pythagorean identity. So remember, our Pythagorean identity says that sine squared x plus cosine squared x has to equal 1. So how do I use that to simplify the equation that we're given? Okay, and we're usually going to do this by substituting an identity into part of the expression in our equation. So in this case, let's replace the cosine. So let's just write everything in terms of sine. So to do that, I want to take my Pythagorean identity and isolate the cosine squared term. And I can do that by just subtracting a sine squared from both sides. Okay, now that may feel kind of weird because when we talked about identities and stuff earlier, we said you're not supposed to add or subtract across the equal sign, but that's really only something you have to worry about if you're proving or verifying an identity, and we're not doing that right now. So we can go ahead and treat this as an equation. We can subtract things from both sides. So doing that will result in cosine squared x equaling 1 minus a sine squared x. So I'm going to replace the cosine squared x in my equation with a 1 minus sine squared. So if I do that, we're going to have 4 sine squared x plus 2, and instead of the cosine squared x, we're going to write in the quantity 1 minus sine squared x. And that is still equal to 3. From here, we can just use algebra. We can expand the parentheses, distribute the 2. We can then combine like terms. And again, just like we've seen before, try to isolate our sine expression. So we'll have 4 sine squared x plus 2 minus 2 sine squared x is equal to 3. The sine squareds combine together, so 4 minus 2 is going to be 2 sine squared x plus 2 is equal to 3. And then we can subtract 2 from both sides. So we have 2 sine squared x is equal to 1. We divide both sides by 2. So sine squared x is equal to a half. And you may think that's as far as you have to go, but we do need to take this a step further because we don't have sine, we have sine squared. So how do we deal with a sine squared? Well, it's quadratic, so we could go back to the previous statement, the 2 sine squared x equals 1. We could subtract the 1 over and factor, or we could just take the square root of both sides from what we have right now. So if I take the square root of both sides, right, we're going to have sine of x is equal to the square root of a half. But remember, when you do square roots of both sides, you end up having a plus or minus. So sine x is equal to plus or minus the square root of a half. Now, you might look at that square root of a half and think that does not look familiar. That does not look like one of our nice unit circle angles. But let's simplify it a little bit. So when you take the square root of a fraction, you can take the square root of the numerator and the denominator separately. And so I know that the square root of a 1 is a 1, and the square root of 2 is still just a square root of 2. Okay, so that square root of a half turns out to be 1 over the square root of 2. And I can rationalize that by getting rid of the square root in the denominator by multiplying top and bottom by square root of 2. And so that's going to give me a plus or minus root 2 over 2. So it turns out we actually are looking at a familiar expression. We have the sine x is equal to the plus or minus square root of 2 over 2. Okay. And that's going to actually split apart into two separate equations. So we're going to have sine x is equal to a negative square root of 2 over 2, or sine x is equal to the positive square root of 2 over 2. And just like we saw in our previous videos, we can solve each of these separately. So where is sine negative? So if we're going to look at the sine x is equal to a negative root 2 over 2, we want to look at where sine is negative. That is in the third and the fourth quadrant, right? They have to be at pi over 4 angles, so that means we're looking at 5 pi over 4 and 7 pi over 4. And if we switch over and we look at the other equation, sine x is equal to a positive square root of 2 over 2. That's, again, the same thing, but now sine is positive, so that's in the first and second. So that's at pi over 4 and 3 pi over 4. Okay, so all four of those angles are going to make sine either equal a positive or a negative root 2 over 2. And so all four of those are going to be our solution in this case. So x is going to equal pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. And that is my solution, again, on the 0 to 2 pi interval. Okay. Now, if I wanted to then express what the infinitely many solutions are, just like we've seen this already, we can add a plus 2 pi k to each of these. Right. So I'm going to have to write out x is equal to pi over 4 plus 2 pi k, 3 pi over 4 plus 2 pi k, 5 pi over 4 plus 2 pi k, and then 7 pi over 4 plus 2 pi k. Right, and that will work. Okay, so that's representing the infinitely many solutions that we have. Now, I can simplify that actually. It turns out if we look at those four solutions on the unit circle, right, each one is in the middle of each quadrant. They're at all the pi's over 4. So 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. How far do I need to travel from the first one to the second? How far is it from pi over 4 to 3 pi over 4? It's a distance of 2 pi over 4, right? From 1 pi over 4 plus a 2 pi over 4 gives you 3 pi over 4. Well, how far is it from 3 to 5? Same thing, 2 pi over 4. And from 5 to 7, same thing. And from 7 to what would be coterminal with pi over 4? 9 pi over 4. So how far is it from 7 to 9? 2, right? So every time, if we started at that pi over 4, we could always get to the next solution, and we could keep going around and around and around by adding just a 2 pi over 4, which 2 pi over 4 simplifies down to pi over 2. So I could take all four of those answers, the pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, all plus 2 pi k, and I could rewrite them as a single expression. We'll just start with the first one, the smallest one. And how far do I have to go from that one to the next? 2 pi over 4, which is pi over 2. So I can say x equals pi over 4 plus pi over 2k. So that one expression gives me the same values, the same set of solutions as that full, as doing all four of them with the plus 2 pi k. All right, let's try another example. This time we are looking at the sine of x is equal to the cosine of 2x. And right off the bat, this cosine of 2x is telling me I'm thinking double angle identity. Okay, and double angle for identity for cosine, we have three options, right? Cosine of 2x is equal to 2 cosine squared x minus 1. It's also equal to 1 minus 2 sine squared x, and it's also equal to cosine squared x minus sine squared x, right? So which one do we want to pick? Well, we want to pick the one that will work nicely with a sine x. I don't have to include a cosine squared and a sine. So let's use the one where we're only involving sine. So that cosine of 2x is equal to 1 minus 2 sine squared. And I'm going to replace that cosine of 2x with that 1 minus 2 sine squared. So we're going to have sine of x is equal to 1 minus 2 sine squared x. This is just a quadratic equation. We have a sine squared, and we have a constant term. So let's write it as a quadratic equation, and then we should be able to factor, or if not, we can do the quadratic form. So let's move everything to the left side so it's equal to 0. So we'll have 2 sine squared x plus sine x minus 1 is equal to 0, right? So I added the 2 sine squared and I subtracted the 1. If it factors, we'll have factoring a trinomial into 2 parentheses that are equal to 0. The first term in each parentheses have to multiply together to give me a 2 sine squared. So that means one of them is probably going to be a 2 sine x, and the other is just going to be sine x. The second value in each of these parentheses has to multiply to give me a negative 1, which means they're both going to be a 1. One of them has to be a plus 1, the other has to be a minus 1. To figure that out, where the plus and the minus go, we need to look at what would happen if we FOILed the parentheses. So if I FOILed this 2 sine x times the 1 and then the 1 times the sine x, I need the bigger value there, the bigger result, to be positive. And so that bigger result is the 2 sine x, and then the 1 sine x would have to be the negative. So I'm going to make the sine x plus 1, and I'm going to make the 2 sine x minus 1. All right, so we can then take each of those factors, break them apart, and set them equal to 0. So we'll have 2 sine x minus 1 is equal to 0, or we'll have sine x plus 1 is equal to 0. We can then, solve each of those. They're just linear equations, so we can solve them. So for 2 sine x minus 1 equals to 0, add the 1, divide by 2. We get sine x is equal to a half. And for sine x plus 1 equals 0, we're going to get sine x is equal to a negative 1. So where is sine equal to a half? In the first and the second quadrant, right? At pi over 6 and 5 pi over 6. So I'm going to get x equals pi over 6 and 5 pi over 6. Where is sine equal to a negative 1? Well, again, that's going to be down on the negative y-axis. That's the coordinate 0, negative 1. And so we're also going to have x is equal to 3 pi over 2 as our solution. So pi over 6, 5 pi over 6, and 3 pi over 2. Those are the solutions on 0 to 2 pi. If we wanted to express them as the infinitely many solutions, we just take each of those and we add a 2 pi k. So x would be pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, and then 3 pi over 2 plus 2 pi k. Okay, so that's how we can express the infinitely many solutions. Now, it does actually turn out that those 3 answers are all equally spaced away from each other. So just like the previous example, we could figure out, we have first quadrant, second quadrant, and then the y-axis. So they're all spaced out an even distance from each other. It's 2 pi over 3. So we could rewrite that as x equals pi over 6 plus 2 pi over 3 times k. and that would give you the same solution set, just in a simpler format. But it's not necessary. All right, let's try one more here. This one's a little more involved of an equation, but it will turn out to not be too bad. We have 2 times the cosine of 4x times the cosine of 3x equals 1 minus 2 times the sine of 4x times the sine of 3x. So you might look at this and just not even be sure where to start. Okay, so some things to look at. We have we have a cosine times a sine. So you might be thinking like a cosine of A, cosine of B, right? You might be thinking a product to some identity. We also have a sine of A and a sine of B. So again, you could be thinking I have to use a product to some identity twice, and you can, it'll work. But if we were to take that minus 2 sine 4x plus sine 3x and add it to the other side, it would look a lot like this: cosine of A plus cosine A cosine B plus sine A sine B. And notice in both cases, the A's are both 4x's, the B's are both 3x's. Well, that is a sum and difference identity. Cosine A cosine B plus sine A sine B is actually equal to the cosine of A minus B. So instead of doing the product to sum identities twice, we can actually just use a sum and difference identity once, and it's going to streamline this whole problem into one nice little expression. So let's do that algebra first. So we're going to add the 2 sine 4x sine 3x to both sides. So we're going to have 2 cosine of 4x cosine of 3x plus 2 sine of 4x times the sine of 3x, and that is equal to 1. Now, as we look at this equation, it doesn't perfectly match the identity just yet, and that's because we have the 2's that are in front of the cosine term and in front of the sine term. But they're both 2's, which means we can factor a 2 out, and then we can divide it over. So we're going to have 2 times the quantity cosine of 4x cosine of 3x plus the sine of 4x and the sine of 3x, and that whole expression is equal to a 1. And so we can actually go ahead and do our identity now. I know that the cosine of 4x cosine of 3x plus the sine of 4x cosine of 3x is going to equal a cosine of the quantity 4x minus 3x. And so all of that is now just equal to 1. So I've taken this big, long expression, and I've been able to reduce it down using our sum and difference identity, to a single cosine expression, which I can simplify. So to take it to the next step, again, we can divide both sides by 2, and we can go ahead and subtract the 4x and the 3x. So we're going to have the cosine of 4x minus 3x is just x, and so that is now going to equal a half. So cosine of x is equal to a half. Well, where's cosine equal to a half? In the first and fourth quadrants. All right, and so that's just unit circle. We know x has to be pi over 3 or 5 pi over 3. Again, that's those are the 2 specific solutions on the 0 to 2 pi interval. And if we wanted to express the infinitely many, then we can just we can add a plus 2 pi k to each of those. So pi over 3 plus 2 pi k, or 5 pi over 3 plus 2 pi k.